So last time we started to talk about basic computation in Python. Maybe we should dim the lights a bit more. Is the font size okay? All right. Right, so we look at ways to define procedures. And we said at that time that they're pretty much mathematical functions, right? We're going to see later that they're a bit more than that. But for the time being, it's fine to just assume that they are mathematical functions, right? We discussed why is it useful to have them, right? And what we said is that it's a means of abstraction. Abstraction means hiding information, right? Why is it good to hide information? Not because of secrecy reasons, but because you, in day-to-day life, have to deal with information overload, right? So you want to overlook some information for a while and focus on the big picture, right? This is what abstraction in programming is. And procedures are something like that, right? We can give a meaningful name. This one is not very meaningful, but we can give a meaningful name to a very complicated piece of computation that has a lot of details. And in that way, we can actually get a sort of a big picture description of an operation that we can use in building other even more sophisticated operations, right? So it's sort of like building a house. You probably have seen sometimes big trucks transporting entire house walls, right, on the road with windows and doors in them, right? So the windows and doors are already mounted. So though that door is made up of small parts, but for the purpose of, when they're transported to the site, they act as basic building blocks for a new phase of construction, right? And this is what we want to do. We want to have a hierarchy, and we want to build small bricks, and with them we build bigger bricks and bigger bricks until we build an entire application. Procedures help with that. In the process of building a procedure, we show that one very important thing is to have branching, decision making, right? So we can decide whether to do something or something else depending on the value of a condition. That condition is a Boolean value, and Boolean values are just another way of another type of data, right? Among the types of data that we have discussed. One thing that I forgot to tell you, well, actually, it's a couple of things that I forgot to tell you. One, Python, apart from the kind of data that we discussed, it has several other kinds of data. Like for example, there are complex numbers. I can say 2 plus 3j, all right? And this is the complex number whose real part is 2 and imaginary part is 3. Instead of I, everybody knows what a complex number is? Yeah, okay. So the typical notation for the square root of -1 is I, right? But engineers don't like to use I for the square root of -1 because they typically use it for the electrical current notation, right? So the intensity of the current is denoted by I, so they like to use J for square root of -1. So that's what you have in Python, and you can treat it as a regular type of data. So if you say 2 plus 3j times 3 plus 4j, right, you would get the result. All right. This is not likely to be very useful for us, but it's a feature of Python, and it's one that you should know. Another one is I haven't showed you two very important comparison operators, equal and not equal. Right? So equal is denoted by two equal signs because the single equal sign represents assignment, right? So if I say 2 equals 3, I'm going to get a false. If I say 2 here, I'm going to get a true. And I can compare pretty much anything. So I can say 2 equals true, for instance, and that's a correct expression. Its result will be false, of course, but it's not something wrong. And the opposite of that, the negation of that, is denoted, do you know how? So it's exclamation mark equal, right? So that's not equal. Your expectation might be from other languages that is less than, greater than. So a lot of languages denote not equal like this, all right? Which makes sense. It's either less or it's greater, but it's not equal. This is an error. So remember that. These things you can find very easily in any Python documentation. So let's try to delve into something that into more sophisticated computations, right? Because so I was trying to hit you with the Hanoi problem, but let's do that last. Let's start with simple things. So let's start with factorial. We already have enough of the language that we can build rather sophisticated computations. What's factorial? It's the product of numbers from 1 to n. N factorial is the product of numbers from 1 to n, right? But whenever we say product, that's not a mathematically sound definition, right? So what would be a mathematically sound definition? I'm going to go to the editor window and try to use it here. Right? A mathematical sound definition would look like this. Factorial of n, factorial of 0 equals 1, right? So by definition, by convention, right? And then factorial of n is n times factorial of n minus 1 if n is greater than 0, right? And it's not defined, it is not defined for negative numbers. Actually, we can define it if we want to. Let's just assume that we are not interested. So is this a mathematically sound definition? Does everybody agree that this is a definition, a mathematical definition that we can work with? Yes? Nobody is concerned about it, right? So if I were to compute factorial of 5, right? We're doing math right now, right? So we're going to the definition and we're going to say that factorial of 5 is factorial of, 5 times factorial of 4. Which we're just applying the definition, right? And now we know what 5 is, but we don't know what factorial of 4 is. So let's apply the definition again. So 5 times 4 times factorial of 3, and we at this point should add brackets, all right? Because according to the definition, the operation 4 times factorial of 3 should be performed before the multiplication by 5, right? And then factorial of 3, right, should be 3 times factorial of 2, right? So we're going to keep going like this, right? So this should be 2 times factorial, 3 times factorial of 2. And you understand the process. At some point, I'm going to see factorial of 0 there, and then the definition is going to come from here, and I'm going to get an expression that I can evaluate at that point, right? The symbol factorial will not be in that expression anymore, so it's something that we can fully evaluate, all right? So guess what? The computer can do the same. So we're going to translate this definition into Python, exactly as you see. Okay? And this is what you see. This is the definition, right? Factorial of k. Well, if k is less than or equal to 0, so we're going to assume that factorial of negative numbers is 1, wrongly. But we don't care. We only assume that we're interested in values of factorial for positive arguments. And then else we return k times factorial of k minus 1. Okay? So it is a very simple definition. It computes factorial. Notice the fact that it has a self-reference. The definition of factorial mentions itself inside its own definition. All right? Yes. So this is a recursive definition. We call it recursive. We're not going to delve into the distinctions between recursion, iteration, right? So this is an advanced, a more advanced computer science topic, all right? It so happens that recursion makes use of mathematical definitions more directly. And for me, at least, as I've been teaching computing and programming for a while, I find it a much easier introduction because I can rely on students on your mathematical background. So let's see this working. All right, so we can put this in here, and then we're gonna save it, and we're gonna say test here, save, replace, and factorial of 10, so you should know, sorry, factorial of 5, so you should know that this is 120, right, just to verify with known values. Factorial of 10 is a much bigger number, right? And there's yet a type of data that we haven't talked about, and we're going to see it now. So if I say factorial of 100, you see this very large number, all right? Does that surprise you? No? Yes? No? Why doesn't it surprise you? It should surprise you. All right? So what if I'm going to ask factorial of 1000? Well, so I might not be able to do factorial of 1000 because the recursion depth is 1000, but let's try 900. Okay, so I get the entire number here. So this should surprise you, right? Most programming environments allocate a finite amount of storage for every piece of data, right? The typical amount for integers is 64 bits. All right. How large a number can we store in 64 bits? Well, it's very easy to find out, right? Something is wrong with my mouse. All right. So if I say 2 to the power of 64, this is the number, right? Actually, there's a trick to that. We have 64 bits, but half of the values should be reserved for negative numbers, right? So it's actually half of that. So we're actually only able to store up to 2 to the power of 63, all right? So this is the number that most programming environments allocate for an integer. Actually, this is the number, this is the limit for Python as well, right? So if I take x equals factorial of, let's make it 100 because we don't want to compute, and I'm going to say now type of x, all right? It's still class int, right? But it's a different kind of int. It's what we call an infinite precision integer, right? And this is another nice feature that Python has, and another type of data. So you always have to be careful about these kind of numbers. Why? You see, when I have limited storage, the multiplication of two numbers in limited storage can be considered to take constant time. I have 64 bits multiplied with another 64 bits. So it's at most 64 square operations inside, right? If I have a number of variable length, every time I multiply it, right, it grows bigger and bigger and bigger, and every multiplication takes longer and longer, all right? So you might want to say that this program is proportional, its time is proportional to the number k here, because we have k multiplications, right? But this number that we return as a value is bigger and bigger and bigger, so the multiplications are going to take longer and longer and longer, right? So you have to be careful because this can be a hidden reason why your programs are slow, especially when you crunch numbers. All right. So this is an interesting thing. Let's move on to another interesting computation, Fibonacci. So Fibonacci solved this problem of finding out. So this is the problem. We have a pair of rabbits, male and female, right? In 1 month, the 2 rabbits mature and are able to produce offspring, right? And it takes another month for the female rabbit to give birth to a new pair. And we're assuming that it's always a new pair, right? So now you have 2 pair of rabbits, but one is mature and can produce offsprings immediately. The other one has still to mature for another month, right? So n months down the road, how many rabbits do you have? How many pairs of rabbits do you have, right? So it turns out that at every time, at every moment in time, right, the number of rabbits that you're going to have is the sum of the previous 2 rounds. So that's the problem that Fibonacci solved. This leads to a very interesting series, and we're not going to study the series. You can go on Wikipedia and read about it. It's a series with very interesting properties, but we're just going to try to compute this number. And it's again because at every time you have to look at the previous 2 rounds. It's a natural recursive solution, right? It's something that comes from math, but can be very, very easily implemented in coding. So at time 0, we assume that we have 1 pair of rabbits, and at time 1, we still have 1 pair of rabbits, right? And then, as we move on to the rounds 2, 3, 4, every time we sum up the rounds of rabbits that the previous 2 rounds of rabbits. Okay? So if k is less than 1, so meaning either 0 or 1, then the value is k. Okay, so by convention, we're just going to consider that at time 0 we have 0 rabbits, just by convention, right? Because it just works nicely that way. And then we're just going to sum up the 2 previous rounds. So let's see this working. And we're going to get fib 10. All right, the value is 55. So an interesting question is how long does it take to compute? Fib 10 is quite fast. Fib 20 is quite fast still. Fib 30 all right. So let's change them by 100. The 100 is already quite slow. All right. So if you're going to try to figure out how long it takes, you're going to figure out that the time is also the Fibonacci numbers. All right. So computing the kth Fibonacci number is proportional to the value of the kth Fibonacci number. Okay, better we stop. And this is actually an exponential function. If you go and study, it's an exponential function, right? So it takes longer and longer to compute the result as the argument grows in size, exponentially longer, right? So it's an example of an infeasible computation. And remember that, right? Whenever the recursive function appears multiple times inside, right? That's a smell, right? You can already have the suspicion that this is going to take nonlinear time. All right, and this is potentially a very slow computation. And this is such an example. All right, let's go back to the Towers of Hanoi. So we're going to try to emphasize a little bit the problem-solving side of computing, right? It's not just important to be able to write code, to put your thoughts into code. It's also important to come up with a good solution, with a good algorithm to a problem. How many of you have seen the Towers of Hanoi problem before? 1, 2, 3. Really? So few? All right. So let's take a look at the problem. So we have 3 poles. And on the first pole, we have a number of disks. In this case, 3. But the typical number is actually 7. It's much more typical to solve the problem with 7 disks. All right? That will take very long if we do it manually. So we're going to stay with 3. The nice thing here is that I can actually move the disks from pole to pole. And there's one rule. I cannot take a bigger pole and place it on top of a smaller pole. All right, so if I try to take this one, which is bigger, and place it on top of the smaller one, it doesn't work. All right, so I'm just going to do a new game. And the objective is to move all the disks to the 3rd pole. Okay, and to find the sequence of moves doing that, for doing that. So it's actually relatively simple, right? But what is important here is to understand the pattern. Right? So it's important to understand the pattern. So in order to understand that pattern, let's move on. You've seen me moving 3 disks already, right? If I were to move them to the middle pole, how difficult would that be? Same. Let me show you where I'm going with this solution. Eventually, I don't want to animate the moves because that would be too complicated at this level. I just want to print the sequence of steps, right? So this is a solution. It prints the steps, right? It prints the steps. So if I want to change this solution so that we can move disks from the first pole to the second pole, what should we be doing? Yes. No. So I want a very generic operation. I don't want step by step what should be doing. Can you give me a generic operation that you can do on this piece of text? Yeah. So everywhere where you see 2, you write 3. Everywhere you see 3, you write 2, right? So if you switch these 2, you're going to get a solution, right? So the solution, because of the symmetry of the problem, the solution is very easy to change so that you have different sources and destinations. Okay. So if you saw me moving 3 poles from the first to the 3 disks from the first pole to the third one, you believe that I can move from the first to the second, right? Now, there's another interesting aspect to this problem. How much should I care? Let's say we have 4 disks here. How much should I care about the 4th one if I just want to move 3 disks? How much do I need to care? Do I need to worry about the 4th one if I just want to move 3 disks? It's the biggest disk, so any other disk moved on top of it, it's as if the big disk didn't exist at all, right? So I'm going to say, let's first move 3 disks from the first pole to the second pole. All right? And we know we can do that. We just discussed that we can do that, right? So we switch the second and third pole with each other, right? And we just do that. So once we have done that, I can take the biggest disk and move it to the third pole, right? And then you again saw me moving 3 poles from one pole, 3 disks from one pole to another, right? So you can believe that I will be able to do that as well, right? So let's move them from the second pole to the third pole, all right? So we already have a strategy for writing a piece of code, okay? And this strategy is recursive, and it's also very much related to mathematical induction, right? In mathematical induction, how would you solve a problem for a generic n? you show that the propositions or whatever you need to prove is true for n equals 0, and then you assume that it is true for n, and you try to prove it for n plus 1, right? You try to prove that the truth of Pn implies the truth of Pn plus 1, right? So how does that apply here? Well, I need to move 4 disks. I can already assume that I can move 3. I don't need to care how I'm going to move 3. I can assume that I can move 3. So I'm going to say I'm going to move 3 to the middle pole. Then I'm left with the largest disk on the first pole. So I can move that to the last pole, right? And then again, I know how to move 3 disks, right? So the hypothesis that I used to have in mathematical induction boils down to the fact that I know already how to solve the problem for a smaller number of disks. And this results in the solution that we're going to look at now, right, which is here. So if k is equal to 0, if I have 0 disks, how many moves do I need to move 0 disks from the first pole to the last pole? 0, right? So we don't have to do anything. You see, there's no else, right? So if k is greater than 0, right, I can assume that I can move k minus 1 disks. And I'm going to move k minus 1 disks from pole A to pole pole B using C as an intermediate, right? So when we code, there's also this little trick. I cannot just mention the first and last pole, because I have to tell somehow the program that the middle pole exists as well, right? So we're going to have these arguments. This is the first pole, this is the auxiliary, the middle one, and this is the third one. So this is the destination, C is the destination. So we're going to move from A to B using C as an intermediate. Once we have moved this k minus 1, we're left with the largest disk on the first pole, right? So we can perform the movement from A to C. This is the largest disk being moved. And then, again, I can make the assumption that I know how to move k minus 1 disks, right? So where were they left? They were left here, right? So I'm going to move them from B to C, which was the final destination, the same as this one, using A as an intermediate pole. And this is a solution, right? This is a seemingly complicated problem, but it has an extremely simple solution, okay? So let's see this one working. And you have the link to the game here. So you can go home and play with it. What am I doing? So Hanoi so let's say we want to move 3 disks initially from 1 using 2 as an auxiliary, and 3 is the final one, is the destination. And for some reason it's very slow. There might be something wrong with oh, it might be that because of the recording of the video recording, it suddenly became very slow. Let's try it for a size of 4. Could you estimate how many there would be? So there would be 15, which was, as a formula, would be what?
7 plus 7 plus 1.
Right. So then, 2 to the power of, so for 3 disks, we have 7 moves, right? For 4 disks, we have 15 moves. For k disks, we have
2 to the k minus 1.
yes, to the power of k minus 1. Okay. So check that it's true. It's always important to figure out how fast a program would work, and we're going to touch on that at some point. All right, but it's good to get into the habit of checking. All right. I'm really wondering whether I would rather maybe the fact that I started Fibonacci for such a big number might have done something wrong. Okay, so let's try again. No. Okay, back in the original position. No, still very slow. So it must be the recording. All right, moving on. Is this clear? Is this solution clear? Okay, I want you to notice something else. The original problem said move all the disk from pole 1 to pole 3, right? What did we solve with something slightly different? We said move all the disk from a generic pole A to a generic pole C, right? So we generalized. And generalizing is an important step of problem solving. Very frequently, generalizing makes the problem easier to solve, not more complicated, right? It's counterintuitive, and people tend to think, oh, I don't want to go too general because it's going to be more complicated. Actually, it might simplify things. We're going to see more examples of this. All right. So, well, I prepared the class for people that were a little bit more advanced, but some of you do have a computing background. We have everything we need for Turing computability. Does anyone know what that means? So Turing computability is, at some point people wondered, what is computable? What can we do with a computer, right? And the person who answered that question was actually Turing, the father of computing, sometime in the 1930s. It's actually not very complicated to get Turing computability, right? It's not a very high achievement. The interesting thing is what the minimal amount of stuff you need to have that, right? And it turns out that we already have Python is a very big language, right? But of the Python, whatever we have learned up to this point already gives us that. We can compute anything we want with what we have learned up to this point, right? And the question is, why do we need more? Why do there need to be other elements in Python? Why do we need why is Python such a richer language, so much richer than just this? And the answer is simple: convenience, right? We have to be able to write pieces of software that comprise millions or maybe tens of millions of lines of code. And if we were restricted to this, we wouldn't be able to, because we wouldn't have the right ways to organize the code so that it becomes manageable. All right, but remember that everything else we learn is convenience, essentially. All right, we move into a very important concept, which is called lambdas, and I'm expecting some difficulty in explaining what it is. So bear with me, and feel free to ask questions, and if I'm going to fast, stop me. So we've seen quite a few types of objects, right? We've seen integers, we've seen doubles, we've seen strings, and we've seen truth values, right? And all these essentially stand for themselves. I don't have to give them a name to refer to them, right? The number 3 is the number 3, and the string ABC is the string ABC, right? But for procedures, for functions, We cannot define, so far with what we've learned, we have not defined a function without giving it a name. Right? We've defined Fibonacci, we've defined factorial, we've defined Hanoi, and we had that computation, that piece of computation needed a name to exist. All right? So all of them are objects. Why is there this discrimination? Why some objects need to have a name and some don't? Right? We should make it so that everything is the same. So if we have the ability to create objects that don't need a name, it should be the case to do that. We should be able to do that for functions and procedures as well, right? So the lambda notation is one such thing. It allows us to define a function without giving it a name. We call these anonymous functions. So think of the following English phrase: the function that increases its argument by 1, that increments its argument by 1, right? I've told you what it does, and it doesn't need a name. This phrase alone tells you what a function does. I don't need to call it inc. I could, if I wanted to, but I shouldn't have to, right? So this is the concept that we're trying to push forward. And this is such a function. What you see in these brackets is the function that increments its argument by 1, right? The result is the argument incremented by 1. So if I take this object and put it into Python, we're going to get something that is not an error. All right? Unfortunately, we won't get something very descriptive either. X plus 1, and we get something that is not an error. Right? I have the option of giving this a name if I want to. All right? And now, if I say f applied to 2, I'm going to get 3. All right? But I can simply do lambda x plus 1, and I apply this to 2, and I get back the same 3. Okay? And there are two important things here, right? One is that functions are just objects that don't require names. But then functions are just objects. They are things that I can manipulate as if they were numbers. All right. So, for instance, I can define this function f applied to 10. Let's say. Not too many, though it wouldn't make a difference. Okay, so this is a function, and guess what happens if I apply this? What should I apply it to? So I want to put something in within the brackets. What should I apply it to? Should I put a number there? No. All right, let's call this G. Make it less confusing. It might get confusing, right? What could I put in there? Could I put F? Remember, F has just been defined. Would it be okay if I put F here? So obviously, if I try 10, I'm going to get an error, right? Right? Why? Because you see, this 10 becomes this G. So then I'm going to have 10 applied to 10 applied to 10. And that doesn't make sense. But if I put here F, remember F is what we have defined up here, right? Then I'm going to get F applied to F applied to 10, which will result in 12. But I don't have to have a function that already has a name. I can just say lambda x plus 1. Okay?
If you use the G in there, would that not be easy because you just defining G?
But this G is bound. right?
Can
So
you add n with g instead of lambda x?
there's no g, right? So if I try to evaluate g now, there's no g. G doesn't exist. All right. So let's translate this into what you're comfortable with. All right. So I am going to call this twice. So what if I say twice, def twice, applied to g, and I say return g applied to g applied to 10. And if I say now twice applied to f, I get 12, right? So I'm applying f twice. So based on this definition, you wouldn't expect that g would exist in the global environment, right? So if this doesn't give a definition to g, right? G is not defined. So if this doesn't give a definition to g, then neither should this, because these two are exactly the same thing. All right, these two, this thing, not the entire expression, just this part, and the definition of twice, they're exactly the same thing. But in the second case, I was forced to give a name to the function, because this is what def does, forces me to give a name, right? The lambda expression doesn't force me to give a name to the function, right? But still works as an object. So if I want to give a name to it, I can use this and give it a name. Does this make sense? Okay. So the important thing is that a function is just an object. It can become the argument to another function. All right? And every function in Python has this property. For instance, let's take the sinus function, and let's get pi as well, because I don't like to write 3.14. All right. So a sine of pi divided by 4 is square root of 2, right? Square root of 2 divided by 2, right? So what if I say twice applied to sine?
From math and
Oh, we haven't talked about that, right? Yeah, a good point to introduce that. So um, Python alone is not very helpful, right? Um, especially to people who are not computer scientists. And in order to be able to have power, to have computational power, we rely on libraries. It's code that other people have written, right? And we can use it readily. These libraries are organized in what we call modules, right? And we don't want all the modules to be loaded up front, because that takes a lot of memory. So each module will take some memory, will take some resources. So we want to only load what we need. There's a huge load of modules. One of the most useful one is the math module that contains all the typical, very common mathematical functions and some of the values of the constants, right? So also, we don't want to import the entire module, again, because of we're worried about resource consumption, right? So inside the math module, there's the function sine and there's the constant pi, and we load them, right, whenever we need them. Yes. Yeah, but typically in this file, I would just write it here, right? I would say import. So there's many ways I can do it, right? From math import sine and pi, right? And at that point, every time I load the file, I don't have to type it by hand, right? Every time I load a file, it gets loaded. Then I can also import everything from that module, right? But then you may argue that it pollutes the global environment. There are so many names that they may clash with some of the functions that you want to write. And then you also, when you write this star, you don't know what you're importing, right? So the good programming practice dictates that you import everything explicitly, so you're always aware of the stuff that gets into your global environment. You can also do just this. And then, if you do that, everything later, right, you can say x equals math dot sine of math dot pi divided by 4. Right? So that is even more protective because it will make sure that it doesn't clash with any other name pi that you might define elsewhere, right?
You don't need
You don't need?
semicolons after that? You don't need semicolons after that?
It's Python. I know that Java likes semicolon. Python does. All right. So are we clear now? Okay. So sorry about overlooking that. So now, what if I apply twice to sin, to sine? Okay. So we're going to get sine applied to sine applied to tan. Right? See the same result. So sine is just another lambda, essentially. It's just another function. It's not just another object function. If I evaluate sine on as a standalone symbol, we get built-in function sine. This is very similar to what we've seen here, function lambda at, right? So it kind of tells us that these two objects are of the same type, the same kind of category of symbols. Okay? Okay. So notice, at least for the time being, so we're going to see some differences between lambda and def later, but for the time being, right, this lambda that you see here highlighted and this definition, they're pretty much the same thing, right? So if I decide to say g equals lambda x plus 1, these two definitions of g are indistinguishable later, right? From the value of g, you cannot tell how they were defined, whether one was defined as a def and the other was defined as a lambda. Okay? They behave exactly in the same way. All right. Now, for those of you who like puzzles, which will not be the majority of you, you should tell me why this works, but not now. I'm not going to go into this, right? So forget about defs. We had defs, and we said that they make the language Turing complete. Forget about defs. Take lambdas instead. We're still Turing complete, right? So previously with defs we had recursion. With lambdas we don't have recursion because it doesn't have a name. Therefore, I can't refer to it, right? But then look what we can do, just as a very basic idea. So this will not be on any test or anything. If you don't want to understand it, don't worry. We can pass the function. We can take a copy of the function. So you'll notice that this and this are exactly the same thing, right? So I can't have a function referring to itself, but I can take a copy of itself through cut and paste and pass it to itself and create a repetitive computation, right? So this computes Fibonacci pretty much as Fibonacci was computing, right? So I don't have the ability to refer this f to refer to itself, but this f refers to the copy that I'm passing in here, which is exactly the same thing, and therefore this just works. These are more philosophical questions. Why did I change x if? Yeah, I didn't. Initially, I called it x, and then I figured that an integer should be called n. But then when I cut and paste, when I changed, I didn't change the. There's another x. All right. Just remember it as an aside. So again, makes the point that it doesn't take a lot to have Turing computability, okay? And you should think about, yes,
Isn't that knowledge is
yeah, it does. So yeah, you need to pay attention from this point on why we need whatever else we introduce. Why do we need that? What does that buy you, right? In most cases, it's convenience and ability to write large programs. Okay, so we toyed around with functions, right? And let's see some examples where it's really useful to have functions as arguments, right? You've seen functions as arguments, but those were toy examples. So one function that needs to take another function as argument is the derivative, right? So how do we define the derivative? Typically, it's defined as a limit, right? But remember, so you're very used to saying the derivative of sin x. That x has no place there, right? What you've learned, the fact that um, that we've learned, and actually I've learned that in school as well, right? So I would say sin x, and then the whole thing would be prime, right? But who's x? Yes. We'll see that there are some differences. So most typically you use def because most typically you actually want to name your functions, right? Most of the time you use def. And why do you name your functions? Because you want to give them a meaningful name that makes the computation easier to understand. Right? It's much easier if you have a function called Hanoi, and from your historical learning experience, right? You know what Hanoi is. You're more prepared to look at the code inside and understand it, right? So the name of the function somehow documents the computation, but there are very many situations where what you need is just one on-the-spot computation, right? That has to change things a little bit, and you want this anonymous function to which you don't want to give a name, right? So that's pretty much when you want to do that. There is another situation which you'll probably not see in this course, is when you want to assemble functions from pieces and actually create a very large lambda, right? It's sort of like compiling a language into another language, right? And the target language would be a big lambda in Python that performs a computation. It's very much used in domain-specific languages, right? Domain-specific languages are just little small languages that solve a very domain-specific problem. They're used in finance mainly, and the way to deal with them is to take a string which represents the language, the DSL, the domain-specific language, and compile it into this lambda, which is actually very large, but it is programmatically built. You never see it. You never see it in a piece of text, right? You don't see it in your program. You just make it up from little pieces until it becomes this big lambda. And then you evaluate it, and then you get the result, which is the execution of the original DSL. All right, and this is where lambdas are most useful. In fact, this is why the technique is very useful. Okay, does that kind of give a hint? Okay. So in this, when we're saying sine x, derivative of sine x, right? The x there has no good place, right? Because which x do I take? X equals 0, x equals 10. There's an infinity of values, right? So what we should actually be saying is derivative of sine. Sine as an object has a derivative which is cosine. Is this understood? Right? So the derivative doesn't take a function of an argument. It takes one function and returns another function. We want to return another lambda. So this is what we're trying to do here. Right? So we want the derivative of of f, which is a function, in a point x. And obviously, we can't compute a limit. So we're going to take a tolerance, right? We're going to approximate it as the ratio of the two differences, right? So we're going to say that it's f applied to x plus epsilon minus fx divided by epsilon, right? So we are computing the derivative in a specific point. Let's see how this works. F5, okay, and we're going to say, and since we're here, I'm just going to import everything, which is acceptable now. So let's say derivative of sine in, let's say pi divided by 4 with an epsilon of 0.001. Okay, so we get a value, right? And we know that the derivative of sine should be cosine. So if I say cos of pi divided by 4, I should get something similar. And you see that it's not very far from there. The smaller the number, you might think that the smaller the number, the better the precision is going to be. But actually, dividing numbers, this number is going to be very, very small. The division, the denominator of the fraction is going to be very, very small, and that leads to actually more errors. So in general, we don't want to make that number very, very small. But the question is now, we were saying that the derivative is a function. It's the function cos, right? But we have wrongly defined this derivative to accept the argument and return a value rather than a function. So how should we change this? I would like the derivative of sine to be cosine, not cosine of pi divided by 4, pi over 4. So what should we return here?
Get rid of x.
Get rid of x, good. So how do I get rid of this x?
Just remain out.
How about this? I don't know what f is, so I'm not, but this is a function now, right? So if I evaluate this, right? So now I'm going to say approximation of cos is this, right? So now I can say approximation of cos applied to p divided by 4 and get the value, right? Or I could go directly and say derivative of sine and 0.001 applied to pi divided by 4. Okay? Is everybody okay with this? What do you mean? Can you? So you're suggesting what, this? And this? All right, so the derivative of sine is cosine. And when I tell you that, where's the x? So this is an English phrase, which is, mathematically sound. The derivative of sine is cosine. And I didn't mention any x in there. Why should I have an x in the definition? Why should I have an x here? Why should I have the x there? What purpose does this x serve? So remember, the derivative of sine is cosine. There's no x, right? The derivative of the logarithm is the inverse function. There's no x in there, right? The derivative of the second order polynomial is the first order polynomial multiplied by 2. No x's, right? So when you say a function, I don't have to say a function of a specific value. It's the function, right? It's essentially the entire correspondence between an argument and the value of the function for that argument, right? So the function is an object, right? So in math, this mistake is often made, right? Because the argument is put there. You're talking about f of x and not about f, right? And x is understood of being this generic thing, but you see, if you translate that into a computation, that x can be generic. Every symbol has a value, right? I can't make it generic. Right? So, yes?
Within the function, we define x as this, f of x, and then at the end we'll return x. Because then x will be function.
Do you want to come and type? What?
Okay. Just get rid of the return over there
Okay.
and the lambda. And you type define there.
Oh, you want to type define here.
Yeah, and then at the end
So I'm going to define d applied to x.
Okay.
Return still needs to be here, right?
And then at the end you start return d.
Yeah. Same thing. It will work, yes. So what you essentially, so previously, let's look at what previously we had. So let's put in that in a command. So previously we had lambda return blah blah blah, right? Instead of the d. So what you have forced here is a name, given a name to the function. Right? So that was previously there. So you've taken this function, this lambda, and you've given it the name d. That's all we've done.
But still, d won't be usable, right?
D won't be usable. D is hidden inside, right? So we're gonna get there when we talk about scope, right? We can have this hierarchical definition. So what's defined inside the function is not visible outside of the function, right? We're gonna see that probably next time. Is this okay? Right? And instead of doing this, I could have done this. Exactly the same thing. Okay? So now I can tell you one distinction between lambdas and defs. Inside lambdas, we cannot use assignment. I cannot use the equal sign. All right? So that's a very serious distinction. It's going to boil down to having side effects. We're going to talk about that a bit later. But remember that they're not the same because you cannot use the equal sign. Okay, so does this make sense? Oh, because again, so the derivative of sine is cosine. And when I tell you that, I haven't used the word I haven't used the x. So it's conceptually important to have that the derivative of a function is another function. But I don't want to, maybe not now, right? So I'm going to pass that to another piece of computation, and that piece of computation will be responsible for materializing the value, right? Whereas if I put the x right here, right now, I am forced to materialize the value. I may not know at this point the x. The only thing I know is the f. And only later I'm going to find out what is the x in a different piece of computation, from a piece of data that comes from somebody else, right? So conceptually, it's important to look at derivative as being, it's a transformation from one function to another function. What I want to give you back is that function that represents the result. Okay? All right. Yeah, so you can take this and play with it. All right. Let's look at something even more sophisticated. Bisection search. So again, this is a very well-known method. There is this thing that we call approximate solutions to equations. And the way bisection search works is very simple. Let's say we have a function. We have an interval such that the signs of the function at the extremes of the interval are different, right? So in this case, at the limit a1, at the lower limit a1, the function value is positive. At the higher limit, upper limit of the interval, the function is negative, right? Their product is negative, they are opposite. So there is at least one root, if the function is continuous, of course, right? There is at least one root between a and b, right? But we're going to work with the assumption that there is exactly one root. So this method only works if there's exactly one root between them, right? And what do? Well, we halve the interval, we go to the middle, which is this b2, and we check the sign of f, right? If a1 and b2 have opposite signs, then the root is between a1 and b2. If b1 and b2 have opposite signs, then the root must be between b1 and b2, right? So we have halved the scope of the root. And we keep halving and halving and halving until we the two limits get so close, right, that they are within our tolerance, and any value in between can be considered a solution, right? So we're going to try to express this computation. So let's see how that works. All right, so we're defining bisection search, again, recursively. We have a function f, we have a low limit, we have a high limit, and we have a tolerance, right? There's a median, which is our first approximation for the root. And there's the function, the value of f at the median, at the median, which is this v. If v is 0, we have already found the root, right? And we can return m. So also it is the case that we have found a good approximation if the distance between high and low is very small. It's smaller than the tolerance. As soon as the difference is smaller than the tolerance, we can actually say any value between h and l is a good solution. It might as well be m, so let's return that. Otherwise, if v and the function value at the high limit are opposite signs, have opposite signs, it means that the root should be between median and high, right? So now we have a completely new problem. We're not different from where we started. We just have a new problem, just that the low limit is m and the high limit is h, right? So we take advantage of recursion. What does this function do? Well, it solves the solution. It provides the solution for a given h and a given l and a given h, right? So I have a new problem. The low limit is m, the high limit is h. So let me just start afresh, but with the low limit being m. All right? The second step is no different conceptually from the first step. Is this clear? So I'm going to reset the low limit to m. The high limit remains h. F and t are the same. It's like starting afresh, but this time my interval is low. Else, what is left? Obviously, this thing cannot be 0 because v is not 0, right? So then we will, it's likely that the solution is between m and l and m, right? Let's put them in increasing order. So then I have a new problem, right? It's completely as at the start, just that my interval has shrunk to L and M. So I'm going to try to find a solution between L and M. All right? Is this clear? So let's keep the math inside. And well, we need a good function because not all functions will work well. So exponential minus 10 is a function that will have a root between 0 and 100, right? You kind of know how the exponential works, right? So exponential is strictly positive, right? But if I lower it by 10 units, it's going to intersect the OX axis somewhere, right? Somewhere in the positive range. So it's definitely between 0 and 100, it will have a solution, right? So let's see if we can find that solution. Right? And this is the solution. We can try to we can check whether this is true, right? So I can take this function and apply it to this value. And we get a value that is reasonably close to 0, right? And let's make this a bit. I'm going to sorry. I'm going to erase this, and I'm going to put the entire expression here. And one thing I would like you to see is if we play with the tolerance, right, that we get better and better, right? So we get the same thing because what we've done is this was the result of this, right? So we just put the expression inside the brackets and we're getting the same thing. But now, because I have this expression, I can go here and play with the tolerance. So I'm going to make the tolerance a bit smaller, right? So you see an even smaller number. This guy here is even smaller, right? And oops, I can make it very, very small. Let's say I can make it 1e minus 200. Oh, everybody is comfortable with the scientific notation? So this is 10 to the power minus 200, right? Everybody knows that. No? So instead of writing 1 to 3, all right, let's go somewhere. Instead of writing 123.4, you write 1.234 E2, right? So that's scientific notation. You always have one digit before the decimal point, right? And then you use an exponent here that is appropriate for the computation. So instead of writing 0.000123, you're going to have 1.23 e minus what, 4, right? So this is a scientific notation. We don't have to write 200 zeros to write a number that is 200 orders of magnitude below 1. Okay? So this is a very, very small number. And actually, what we can do is go up to minus 308, right? But I want to still be conservative. And what happens now? Oh, come on. What do you think happened? You get this, right? Maximum recursion depth exceeded. What do you think this means? All right. What do we mean by too much recursion? Again? I can.
It goes on forever.
Not forever. It right. So it goes on for longer than there is storage for it. Not forever, right? So we know that it stops for reasonable numbers, right? But there is a certain amount of storage where we can store delayed computations, right? When we discussed factorial, I showed you that we start with 5 times factorial of 4, and then factorial of 4 becomes 4 times factorial of 3, right? 5 times 4 times factorial of 3. One important thing that happened here is that we have this bracket, right? Because we have to compute factorial of 4 before multiplying with 5. Now imagine that this is 500 and this is 499, right? So this chain, the expression will have 500 elements, right? 500 numbers in it, right? There will be 499 delayed multiplications, all right? Before we can reach to something that can be evaluated. If this number is 5,000, well, let's make it 50,000, right? This is 49,999, right? You're going to have 49,999 delayed operations, right? This will take storage inside the computer's memory. And at some point, the amount of storage that the Python is willing to give you is exhausted, right? There's a setting that can change that, but that setting, you should never tweak it, right? So what we should do is actually get rid of recursion, and we're going to learn this next time. All right, but so be aware, whenever you write recursive functions, this is one of the dangers. Let's put something here that is a bit more. So I'm going to put minus 50. This should work. Oh no, it doesn't. I tried with a reasonably low value at home. I can't remember what it was. Maybe minus 20. Let's try minus 10. Okay, so this should work, right? So you see, so this is essentially we're not showing here the actual value. So another thing that would be interesting to see here would be the value of the solution, right? And how does this differ from the value of we had minus 4 here, right? So you see, they're not differing very much, right? But as we make the tolerance smaller, the closeness, what we're looking is a solution to function equals 0, right? The equation is function equals 0. So this is the value, this is how far from 0 we are, right? We're getting closer and closer to 0. So as we decrease the tolerance, as we request more precision, right, we are getting better results. But you see that in terms of moving around this number, the number is already quite good. We're not seeing a lot of movement around it. We're still up to about 5 decimal places are correct. Between tolerance minus 10 and tolerance minus 4. So it's not always worthy to ask for more tolerance, right? Increased tolerance doesn't give you necessarily a much better solution. Yes, that's true. So because we are working with the exponential function, that's true, right? So if you worked with a polynomial, you would probably get more bang for the kick. All right, but always be aware. So look at the function that you want to solve. Before trying a very complicated, a very computationally intensive piece of computation, figure out whether that's necessary or not. All right. Okay, so this hopefully gives you something to play with. All right, so we're going next time. We're going to start learning non-iteration, right? Non-recursion, which is iteration. We're going to start talking about while loops, and we're going to rewrite everything we've written just now in terms of while loops and get rid of recursions and get rid of this potential danger of exceeding the recursion depth. We'll see how that goes. Let me know whether the pace today was better, too fast, too slow. If you have any questions, yeah, feel free to ask me over email. Any kind of feedback, yeah, just